Welcome back to Calculus AB, everybody. Today's topic, we're continuing with 3.1. This would be part 3. So we're looking at the trigonometric functions and the chain rule. So the chain rule versions of the derivatives of the 6 trig functions are as follows. So you guys are going to have pretty much the derivative of sine is going to be equal to, again, cosine of u times u prime. So whatever u is, you're going to take the derivative of that, and then you're going to multiply it times the derivative of sine of u, right? So same thing. So tangent of u is equal to secant squared of u times u prime. Secant of u is equal to secant of u times tangent of u times u prime. And then cosine of u is negative sine of u prime times u prime. Cotangent, negative cosecant of u times u prime. And cosecant is negative cosecant times cotangent times u prime. So now we're going to see how we're going to apply these. So again, we're still using the same process, right? We're identifying the internal function and the external function. Now, in the following examples, the external functions happen to be the trig functions, right? Sometimes it's backwards, so you guys got to be careful. So here we're looking at problem A. So we want to find the derivative. So first, let's identify the interior function, which is always our u, and that's equal to 2x. Right? If we take the derivative of that, u prime is just equal to positive 2. And then since we know that y is equal to sine of u now, right, with the substitution, right? So we're going to find dy dx is going to be equal to, remember again, the derivative of y with respect to u times, it looks like a y, times the derivative of u with respect to x, right? And that's pretty much that's that one right there. We already have that one. So here we're going to find the derivative of sine of u, which would be cosine of u, right, times 2. And then again, do the back substitution, right? Replace u again. So that's going to be 2 times cosine of 2x. And that's pretty much our y prime. All right, so let's look at B now. So same thing. Again, let's identify our interior function, right? Our inside function. That's going to be u equals. So here is already in parentheses for us. So it's going to be 3x minus 1. U prime, if you take the derivative of that, applying the power rule, we're just going to get positive 3, right? And then, so we want to find, again, dy dx, right? We know y is equal to cosine of u. Right, let me move this. So dy dx, right, again, is equal to the derivative of y with respect to u. That would be the derivative of this part right here, times the derivative of u with respect to x, which is, again, u prime, right? So here we find the derivative of cosine with respect to u, which is negative sine of u, and then times u prime, which is just 3. Do the back substitution, right? Replace the u with what it represents, which is 3x minus 1. So that would be negative sine of 3x minus 1. Actually, let me put the 3 in front now. So negative 3 times sine of 3x minus 1. And that would be our dy dx. All right, and then the last part right there, part C, we're looking for pretty much, again, our interior function, our inside function. So u equals 4x. That would be du dx, right? The derivative of u with respect to x is equal to just positive 4 once we apply the power rule. We know that y equals secant of u now, right? With the back substitution, we substitute u. All right, and then, so again, dy with respect to x, dy dx, equals the derivative of y with respect to u times the derivative of u with respect to x. So again, we have this part, right? We have du dx, that's just our u prime, or actually labeled it the same thing. So 4, so times 4 And then the derivative of secant pretty much gives us secant tangent, right? So secant of u times tangent of u, all right? And then again, resubstitute without the u, right? You want to get rid of it. So that would be secant of 4x times tangent of 4x times 4. So I can put the 4 in front now, times. There you go. All right. And then let's continue the next part. Zoom out a little bit. Okay. So example 5. So repeated use of the chain rule. So you guys are not always going to get just one layer of the chain rule, right? You're going to get like a function inside another function inside another function, right? You guys can imagine it like those little Russian dolls, right? Where you have one inside of the other one inside of the other one, and you don't know how many you have, right? Pretty much until you get to the end. So it's kind of the same thing here, right? So it's the repeated use of the chain rule. So here you want to make sure that you identify what's inside of what, and then following along with that. So here, the first thing we want to do is rewrite everything with a parentheses. If I see an exponent on the trig, rewrite it with a parentheses. So this is going to be equal to sine of 3x, and that raised to the fourth power. All right. So now here, since we have pretty much, if you think about it, we have one layer, right? We have our exterior layer is to the fourth power. Our next layer is sine of something in there. And then our last layer, our internal layer, right? The last part about it is going to be 3x. Okay. So now here we're gonna do two substitutions, right? So pretty much we're doing the chain rule 3 times, right? So let's first find the derivative of the outside. So this would be, right? So we're finding the derivative of something to the fourth power. So if you guys can think about it this way, you can block this off, right? The derivative of something to the fourth power is just that. It's 4 times that something raised to the third power, right? And then I know that that something is pretty much sine of 3x. So sine of 3x. Okay, so I did the exterior layer, right? Now I want to do the derivative of the interior layer. So I want to take one more layer off, and that's going to be the derivative of sine. What's the derivative of sine? Pretty much cosine, right? And then again, leave the interior intact, right? 3x. And then my last step here would be pretty much just to multiply it by the derivative of that little inside part, the 3x inside of that. So times the derivative of that, which would be just 3. And then here you put it all together. So 4 times 3, you guys get 12 times sine cubed of 3x, right? Times cosine of 3x. And that would be the y prime or dy dx. All right. Some of these, again, are a little bit to take in. So again, is focus on like taking off those layers, right? Of like, it could be like a gift or something, and you're taking off those layers of wrapping paper little by little. All right. So let's look at example B right there. So again, you guys see a square root. The first thing you should come into your head would be, okay, rewrite it with a parentheses. So that's the secant of x over 2, and then that raised to the 1/2, right? Okay. So again, I'm going to assume this is just like a single unit, right? So what's the derivative of that exterior part of something raised to the 1/2? So I know n is 1/2 times that something, and then n to minus 1/2, or 1/2 minus 1 would be pretty much negative 1/2, right? So again, I remove that layer that I just added, right? Let me rewrite that. So now I look at the inside. The inside remains the same. I put it in there, secant of x over 2. Now I focus on the next layer, which is the derivative of just secant, right? So times the derivative of secant would be secant times tangent. So secant of, again, still haven't taken the derivative of that, and I'm not going to touch it until the end. So secant of x over 2 times tangent of the same thing, right? X over 2. All right. And then times, finally, the last layer, which is this part right here, will be the derivative of x over 2. And remember that x over 2 is just 1/2 times x. The derivative of x is just 1. Then times a half is just times another half. And then combine these three, so you're going to get 1/2 times 1/2. That gives you 1/4. And then pretty much, if you want to rewrite this, this has a negative exponent, so you can rewrite it at the bottom. So secant of x over 2 raised to the 1/2, right? Now with a positive exponent. And then these right here are going to be on top, right? So that's going to be secant of x over 2 times tangent of x over 2. There you go. We don't need that one no more. All right. And then let's look at one more from these. All right. So on this one, again, you see already an exponent right there. So rewrite it with a parenthesis. So this is a cotangent of 3x over 2, right? And then that whole thing raised to the 2/3. So again, block this little thing off right here, right? Block it off. So take the derivative of that part, right? Take the derivative of that. N equals 2/3, right? N minus 1, that's going to be negative 1/3. So I take the derivative of that, whatever's in there, right? And that's going to be pretty much 2 over 3 in the front, right? Y prime, raised to the negative 1/3. All right. And I know what's in there, right? I know it's cotangent of 3x over 2. So I'm going to rewrite it in here. Cotangent of 3x over 2. All right. Now work on the next layer. What's the derivative of cotangent? So times the derivative of cotangent, which in this case would be negative cosecant squared. So negative cosecant squared. And again, that layer inside of it, the last layer, still haven't touched it, right? You do that until the end. So this is going to be 3x over 2, and then times the derivative of the last layer, which in this case is just 3 over 2, right? Using the power rule. So this goes away with that, and this also with that, nicely. So we're left with, on top, we have negative cosecant squared of 3x over 2, and then everything divided by cotangent of 3x over 2 raised to the positive 1/3, right? That's why I'm rewriting it as a denominator. And that happens to be our y prime.